Hello, everyone. Welcome to Sleep Space. Tonight, we'll talk about something magnificent, mysterious, and essential to life itself, our sun. We'll explore the deepest we've ever seen into it and everything we've come to know about this brilliant star that anchors our solar system. Let your mind relax as we take a slow, gentle journey into the heart of our closest star. The sun has been part of human existence since the very beginning. Long before telescopes or satellites, ancient civilizations observed its movements and rhythms, timing their crops, rituals, and even myths to its rise and fall. It was a god, a clock, a symbol of warmth and life, but it was also a mystery. What was it made of? How far away was it? What made it burn so brightly for so long? Today, we know far more than we ever imagined possible. With spacecraft, solar telescopes, and advanced physics, we've managed to peel back some of the layers of this brilliant sphere of plasma. We've gazed deeper into the sun than ever before, not just visually, but through data and inference, through sound waves that echo within its body, through neutrinos that pass from its core to Earth, and through light that takes thousands of years to emerge from its dense interior. Let's begin at the surface, what we can actually see from Earth. The sun's surface, known as the photosphere, is about 5,500 degrees Celsius, or around 10,000 degrees Fahrenheit. That might sound incredibly hot, but it's actually one of the cooler parts of the sun. The photosphere is where sunlight originates. It's not a solid surface like the ground beneath your feet. Rather, it's a visible layer of gas where light can finally escape into space. Imagine looking at the surface of a boiling pot of water, bubbling, constantly changing, cells of hotter and cooler material shifting and flowing. That's what the sun's surface looks like when observed closely, and those bubbles are called granules. These granules are massive. Each one can be the size of Texas, and they last for a few minutes before new ones form. They're caused by convection. Hot plasma rises up from below, cools at the surface, and sinks again, creating a dynamic, ever-moving ocean of glowing gases. The darker regions you might have seen in images of the sun are called sunspots. These are cooler, darker patches that appear where magnetic fields are particularly strong. They can be larger than Earth, and they come and go in cycles. The sun has an approximately 11-year cycle of solar activity, known as the solar cycle. During solar maximum, sunspots and solar flares are more common. During solar minimum, things quiet down. These cycles are linked to the sun's magnetic field, which flips direction every cycle. North becomes south, and vice versa. It's a process that's still not fully understood, but we've been tracking these cycles for centuries. Above the photosphere lies the chromosphere and the corona. The chromosphere is a thin layer where the temperature begins to rise again, and the corona is the sun's outermost atmosphere. Here, the temperature soars to over 1,000,000 degrees Celsius. This is one of the great solar mysteries. How can the outer atmosphere be so much hotter than the surface? It's like standing next to a campfire and finding that the air several meters away is hotter than the flames. Scientists believe that this heating is due to magnetic reconnection. When magnetic field lines snap and realign, they release bursts of energy. This can send waves of heat and particles racing through the corona, creating a superheated environment. These magnetic interactions are also responsible for solar flares and coronal mass ejections, which blast charged particles into space and can affect Earth's magnetic field, satellites, and even power grids. One of the most revolutionary missions to study the sun is NASA's Parker Solar Probe. Launched in 2018, This spacecraft is the closest we've ever sent anything to the Sun. It's diving into the corona, collecting data, measuring magnetic fields, solar winds, and particle flows. Protected by a carbon composite heat shield, it's withstanding temperatures of nearly 1,400 degrees Celsius, while gathering data that no previous probe could access. The Parker probe has already revealed fascinating details about the solar wind, the stream of charged particles flowing out from the Sun. It turns out that this wind isn't as smooth as we thought. It's turbulent, irregular, and shaped by magnetic switchbacks, sudden reversals in the direction of the solar wind's flow. Understanding these phenomena helps us protect astronauts and spacecraft and gives insight into the forces that shape our entire solar system. Now, let's move inward from the corona down to the solar interior. We can't see inside the Sun directly, of course, but just as seismologists study earthquakes to understand Earth's interior, solar physicists use helioseismology, the study of pressure waves traveling through the Sun, to learn about its internal structure. These waves cause the surface of the Sun to oscillate, and by observing these oscillations, we can infer what's happening deep inside. The Sun's interior is divided into several zones. At the center is the core, where nuclear fusion occurs. Temperatures here reach about 15 million degrees Celsius, and the pressure is over 250 billion times the air pressure at sea level. This is where hydrogen atoms are fused into helium, releasing enormous amounts of energy in the process. This energy is the source of all sunlight and heat that the Sun emits. The fusion process begins when two protons collide and, through a series of reactions, eventually become a helium nucleus. In the process, some of the mass is converted into energy, as described by Einstein's famous equation, E at mc2. This energy travels outward, but very slowly. It takes tens of thousands to hundreds of thousands of years for a photon generated in the core to make its way to the surface. It's like a pinball machine, with the photon bouncing endlessly through the dense interior, being absorbed and re-emitted over and over again. Surrounding the core is the radiative zone, where energy continues to travel outward, mostly in the form of radiation. This region is incredibly dense and hot, and the movement of energy is slow and chaotic. Beyond that is the convective zone, where the Sun's plasma becomes cooler and less dense. Here, energy is transported not by radiation, but by convection. Hotter plasma rises, cooler plasma sinks. This is the region that gives rise to the bubbling granules seen on the photosphere. One of the most remarkable confirmations of fusion happening in the Sun's core came from the detection of solar neutrinos, tiny, nearly massless particles produced during nuclear fusion. These neutrinos pass through matter almost completely unimpeded. Every second, trillions of solar neutrinos pass through your body without a trace. By building deep underground detectors shielded from other particles, scientists have been able to measure these neutrinos and confirm the reactions happening in the Sun's core. It was an extraordinary triumph of both engineering and theoretical physics. Our understanding of the Sun also comes from comparing it to other stars. The Sun is a G-type main sequence star, also known as a yellow dwarf. It's about 4.6 billion years old and has roughly another 5 billion years to go before it runs out of fuel. Compared to other stars in the universe, it's fairly average in size and brightness. There are stars much larger, brighter, hotter, and others much smaller and cooler. But for us, the Sun is perfectly balanced, providing just the right amount of energy for life to flourish on Earth. The light that reaches us from the Sun, visible light, ultraviolet, infrared, carries more than just heat. It carries information. Sunlight tells us about the sun's composition, temperature, and magnetic activity. Using spectroscopy, scientists can examine the light and identify the elements present in the sun. We know that it's mostly hydrogen and helium, with small traces of heavier elements like oxygen, carbon, and iron. These small amounts of heavier elements tell a story of cosmic evolution. These atoms were formed in stars that lived and died before our sun was born. Even with all we've learned, the sun still holds many mysteries. We don't fully understand the mechanisms behind the solar cycle, the exact way magnetic fields interact with plasma, or the fine structure of solar wind turbulence. But with every mission, every observation, and every discovery, we go a little deeper. The sun is no longer a burning mystery in the sky. It's a complex, dynamic, living star, and we are lucky enough to study it up close. Let your mind rest in the warmth of that thought. The same star that warms your skin and lights your days is being watched, studied, and understood with tools and minds across the globe and beyond. To understand the sun more deeply, we have to think beyond light. Light is only part of the story. One of the most transformative ways we've learned about the sun is by looking at it across the electromagnetic spectrum, seeing it in wavelengths beyond what the human eye can detect. Each wavelength reveals a different layer or behavior of our star. In ultraviolet light, for instance, the sun reveals the activity of its outer atmosphere, the corona. Ultraviolet imaging shows us solar flares, the dynamics of magnetic loops, and how energy moves in and out of different solar layers. Ultraviolet observations are especially useful in understanding how the sun impacts space weather, those effects on satellites, astronauts, and power systems caused by solar storms. Then there's X-ray observation, which reveals even higher energy processes. In X-rays, the corona becomes dazzlingly bright, and we can observe regions of intense magnetic activity. These X-ray bright points often mark the locations of energy release, magnetic reconnection, and the starting points of solar eruptions. At longer wavelengths, like radio waves, we observe entirely different phenomena. Radio telescopes capture emissions from the sun's magnetic field lines and electron movements. Bursts of radio energy often accompany solar flares, and these signals can help us detect solar events even when they're on the far side of the sun, out of view from Earth. Each layer of the sun corresponds to a temperature, density, and magnetic condition, and each tells a different part of the sun's story. For example, the photosphere emits mostly visible light. The chromosphere emits ultraviolet. The corona, with its million-degree temperatures, emits X-rays. Together, these layers form a dynamic system in constant motion. The sun's magnetic field plays a central role in almost all of this activity. Generated by the movement of conductive plasma in the convection zone, the solar magnetic field is incredibly complex. It doesn't simply loop neatly from north to south. Instead, it twists, bends, and tangles, creating a constantly shifting environment of magnetic pressure and energy. This field forms structures called coronal loops, visible in ultraviolet and X-ray images. These loops are gigantic arcs of magnetic energy filled with glowing plasma. They can last for hours or days, and when they become unstable, they can release flares or mass ejections. At their largest, coronal loops can reach heights greater than 30 times the diameter of Earth. The magnetic field also shapes the heliosphere, a vast bubble of charged particles and magnetic fields extending well beyond Pluto. The heliosphere acts as a shield, protecting the solar system from cosmic rays and interstellar particles. Solar wind, carrying pieces of the sun itself, flows out into this bubble, pushing against the interstellar medium and shaping the boundary where our sun's influence ends and the galaxy begins. Solar wind is made of electrons, protons, and heavier ions, constantly streaming away from the corona. But the wind isn't uniform. There are fast and slow components. Fast solar wind comes from coronal holes, cooler regions of the corona with open magnetic field lines. These allow particles to escape more freely, creating a high-speed stream. Slow solar wind, on the other hand, comes from areas of closed magnetic loops and is more turbulent and variable. When the solar wind reaches Earth, it interacts with our magnetosphere, the magnetic field surrounding our planet. This interaction creates auroras, also known as the northern and southern lights. When solar particles collide with atoms in Earth's upper atmosphere, they excite those atoms, which then release light. The result is a glowing curtain of greens, reds, purples, and blues dancing across the polar skies. Sometimes, though, the sun does more than gently stream particles into space. It erupts. Solar flares are sudden bursts of radiation caused by magnetic energy release. These flares can last from minutes to hours and release energy equivalent to billions of nuclear bombs. They emit light across the electromagnetic spectrum, from radio waves to gamma rays. If directed toward Earth, they can disrupt communication systems, GPS signals, and even airline navigation. Even more powerful are coronal mass ejections, CMEs. These are massive clouds of solar plasma and magnetic fields hurled into space. If one hits Earth, it can compress the magnetosphere and induce powerful geomagnetic storms. These storms can damage satellites, disrupt power grids, and increase radiation exposure for astronauts and high-altitude flights. One of the largest geomagnetic storms in recorded history was the Carrington event in 1859. Telegraph systems sparked, and auroras were seen as far south as the Caribbean. If a similar event happened today, it could potentially cause widespread technological disruptions. That's why scientists constantly monitor solar activity through space weather observatories. Satellites like the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, have revolutionized our understanding of the sun's behavior. SOHO, launched in 1995, has been crucial in tracking CMEs, observing the sun's structure, and even spotting thousands of comets. SDO, launched in 2010, provides high-definition imagery of the sun in multiple wavelengths, capturing events in stunning detail and helping researchers study the sun's interior through helioseismology. The sun isn't just a sphere of gas, it's a constantly changing reactive system of forces. Every second, over 600 million tons of hydrogen are fused into helium in the core. That process releases energy, which slowly works its way outward, carried by photons and plasma currents. It radiates from the surface as light and heat, reaching Earth 8 minutes later. But the light that touches your skin today may have taken tens of thousands of years to reach the surface from the core. It's a journey through extreme density, temperature, and time. A story written in radiation. The photons bounce, scatter, and crawl their way through the sun's interior before finally escaping into space. Interestingly, while we cannot see the sun's core directly, we detect its influence. Solar neutrinos, as mentioned earlier, offer a rare direct line of communication from the fusion zone. These particles travel at nearly the speed of light, passing through the sun and Earth almost untouched. By measuring them, scientists confirm that nuclear fusion is happening just as theory predicts. Our understanding of the Sun is also enhanced by studying solar twins, stars in the galaxy that closely resemble the Sun in mass, age, and composition. By comparing our Sun to these stellar siblings, we can understand how typical or unique it might be. Some stars burn hotter and faster, others are dimmer and longer lived. In many ways, our Sun seems to be just right, stable, long-lasting, and calm enough to support life on a nearby planet. Looking even further ahead, astronomers study stars in different phases of their life cycle to predict the Sun's future. In about 5 billion years, it will exhaust the hydrogen in its core and begin to fuse helium. This transition will cause the Sun to expand into a red giant, engulfing Mercury and possibly Venus. Earth's fate is uncertain, but its surface will likely become uninhabitable long before that, scorched by the growing Sun. Eventually, the Sun will shed its outer layers into space, forming a glowing planetary nebula. What remains will be a white dwarf, a dense, Earth-sized remnant slowly cooling over billions of years. This is the quiet end of a medium-sized star's life. It's a cycle repeated across the galaxy, seeding the cosmos with the elements that form planets, oceans, and life. The Sun, then, is not a static ball of fire. It is an evolving system, shaped by forces we've only recently begun to understand. From its churning interior to the delicate dance of particles in the heliosphere, it is both violent and stable, familiar and mysterious. It touches every part of our lives, from the climate and weather to the functioning of satellites and the rhythms of our biology. And despite all our knowledge, we're still asking questions. Why does the corona heat so much more than the surface? What triggers a flare or CME? How do solar cycles truly work? These questions drive missions like Parker Solar Probe and the European Space Agency's Solar Orbiter, which is providing the closest ever images of the Sun's poles, regions that may hold keys to understanding the magnetic cycle. We are living in a golden era of solar exploration. Every day, data streams from satellites and telescopes that let us peek deeper than ever before. The Sun is no longer just a circle in the sky. It's a laboratory, a puzzle, a living force. We study it not just to understand the universe, but to protect the systems we rely on and to glimpse the story of our own star. The more we study the Sun, the more we uncover the profound connections between it and everything in our solar system. Its gravity keeps the planets in orbit, its energy drives weather and climate, and its electromagnetic influence reaches deep into planetary magnetospheres. It is not simply an isolated ball of plasma, it is the central force that sculpts the very architecture of our celestial neighborhood. Let's begin with gravity. Though we often associate the Sun with light and warmth, its immense gravitational pull is the invisible thread that binds the solar system together. Holding over 98% of all the mass in the solar system, the Sun's gravity keeps the planets, dwarf planets, comets, and asteroids moving in orderly paths. The planets orbit the Sun not because they are attracted like a magnet, but because of the balance between their forward momentum and the pull of the Sun's mass. This interplay between motion and gravity was first described in precise terms by Johannes Kepler and later refined by Isaac Newton. But the Sun's reach goes far beyond the planets. It extends to the edge of the Oort cloud, a vast sphere of icy bodies possibly a light year away. That's how far the Sun's gravity can still hold influence. Though faint, it is enough to keep distant comets loosely tethered to our star, completing orbits that can take millions of years. Now consider the solar wind, the continuous flow of particles streaming from the Sun. These particles fill the heliosphere, an enormous bubble that acts as a shield against interstellar radiation. This solar wind carves out a protective cocoon, shaping the edge of our solar system and defining a boundary called the heliopause, the point where solar wind pressure balances with the interstellar medium. This is the true edge of the Sun's influence. The Voyager 1 and 2 spacecraft, launched in 1966, are the first human-made objects to cross this boundary. As they travelled past the heliopause, instruments recorded a drop in solar particles and an increase in galactic cosmic rays, proof that they had left the Sun's domain. These craft continue to send back data decades later, expanding our knowledge of how far the Sun's reach extends. The Sun also influences planetary environments through radiation. The solar constant, the amount of solar energy reaching Earth, drives the planet's entire climate system. Solar radiation powers the water cycle, stirs the winds, fuels photosynthesis, and regulates surface temperatures. Without this input, Earth would be a frozen, lifeless world. But solar energy isn't evenly distributed. Earth's tilt and orbit create seasons. Different latitudes receive different intensities of sunlight, and changes in solar output, though subtle, can influence climate over long time scales. For example, the Maunder minimum, a period of very low sunspot activity in the 17th century, coincided with a cooling period in Europe known as the Little Ice Age. Though the connection is complex, it shows how variations in solar activity can ripple through the Earth system. Another key link between the Sun and Earth is magnetism. Earth has a magnetic field generated by molten metal movements in its outer core. This field interacts constantly with the interplanetary magnetic field, IMF, carried by the solar wind. When a burst of solar plasma collides with Earth's magnetosphere, it can compress, stretch, and twist it, creating geomagnetic storms and auroras. During these storms, charged particles spiral along Earth's magnetic field lines toward the poles, where they collide with atmospheric gases and create brilliant light displays. Oxygen glows green or red, while nitrogen creates purples and blues. These auroras are not just beautiful, they are physical signs of our connection to the Sun's ongoing activity. To protect modern technology from these events, scientists monitor space weather continuously. The NOAA Space Weather Prediction Center, NASA's solar observatories, and international agencies work together to track sunspots, flares, and solar wind conditions. Warnings are issued when geomagnetic storms are likely, giving satellite operators and power grid managers time to adjust systems and avoid damage. As we reach further into the solar system, with crewed missions to the Moon, Mars, and beyond, understanding solar radiation becomes even more critical. Outside of Earth's magnetic shield, astronauts are vulnerable to solar particle events, SPEs. These sudden outbursts of energetic particles can increase radiation exposure significantly. Spacecraft must be designed to withstand these events, and mission planners must monitor solar activity closely to protect future explorers. Interestingly, the Sun's radiation isn't uniform in time. It follows an approximately 11-year cycle, during which the number of sunspots, flares, and CMEs rises and falls. This solar cycle is driven by the dynamo process, the Sun's internal mechanism for generating magnetic fields through rotating, convecting plasma. At the start of a cycle, sunspots appear at mid-latitudes. As the cycle progresses, they drift closer to the equator. During solar maximum, the Sun is more active, with frequent flares and stormy space weather. During solar minimum, the sun is quieter, with fewer sunspots and less frequent eruptions. At the end of each cycle, the sun's magnetic poles flip, north becomes south, and vice versa. This magnetic reversal is part of a deeper 22-year cycle in which the sun returns to the same magnetic orientation it had two 11-year cycles earlier. Scientists study these patterns to understand how solar magnetic fields evolve and how they might affect both Earth and our space-based systems. The complexity of the sun's magnetism is most visible in active regions, areas with especially strong magnetic fields, where loops and arcs of plasma twist into the corona. These regions often host sunspots and are the origin points for flares and CMEs. They're monitored carefully because of the potential impact on Earth systems. Yet, even in its quietest moments, the sun is dynamic. The corona still dances with fine threads of plasma. The photosphere continues its bubbling convective churn. The solar wind never stops flowing. There is no true off switch. The sun is a continuous engine, fusing hydrogen into helium and sending light and particles across the solar system. From a human perspective, the sun can seem unchanging, rising and setting day after day. But over years, decades, and millennia, it evolves. Its luminosity gradually increases over time, which means Earth's climate will also change. In about 1 billion years, the sun will become hot enough to begin evaporating Earth's oceans, even before it enters its red giant phase. Looking to the distant past, we also find clues in Earth's rocks and atmosphere about the early sun. When the sun was young, it was about 70% as bright as it is today. This faint young sun paradox puzzled scientists because geological evidence shows that Earth still had liquid water billions of years ago. How could the planet stay warm with a dimmer sun? Several hypotheses have been proposed. One is that Earth's early atmosphere had higher concentrations of greenhouse gases, like carbon dioxide and methane, which trapped more heat. Another idea is that the early sun emitted more ultraviolet radiation, which interacted with the atmosphere differently than visible light does today. It's a reminder that the sun's behavior and Earth's response have always been deeply intertwined. Today, we use advanced computer models to simulate the sun's past, present, and future. These models incorporate solar rotation, magnetism, plasma flows, and convection. They help predict solar cycles, space weather, and long-term luminosity trends. Combining observations with simulations gives us a more complete picture, and yet so many questions remain. Why does the solar cycle vary in intensity from one period to the next? What exactly causes magnetic polarity reversals? How does the deep solar interior evolve over time? These are not just scientific curiosities. They matter for understanding our place in the solar system and how to navigate the spacefaring future ahead. The sun is more than just our star. It is a teacher offering insight into fundamental processes of physics, magnetism, fusion, and plasma behavior. Studying it has driven advances in material science, data modeling, and instrumentation. It has also inspired a sense of wonder across generations, cultures, and disciplines. Even myths and stories reflect humanity's ancient fascination with the sun. From the Egyptian god Ra to the Greek Helios, from the Japanese goddess Amaterasu to the solar discs of Incan temples, the sun has always represented light, power, life, and mystery. Today, as we study it with satellites and simulations, we are still participants in a very old dialogue, asking the sun to tell us its story. And the deeper we look, the more the sun responds, not in words, but in light, particles, and fields. Every discovery brings us closer to understanding this immense, blazing sphere that gave us life and continues to shape our destiny. Understanding the sun has always required ingenuity. Unlike Earth, where we can drill or descend to explore its layers, we cannot physically reach into the sun. It is far too hot, too vast, and too dangerous for any probe or material to survive its interior. So how do we study something we cannot touch? The answer lies in interpreting the clues the sun gives us, through light, waves, and particles. Let's begin with one of the most innovative methods, helioseismology. Just as geologists use earthquakes to probe Earth's inner layers, solar physicists use oscillations on the sun's surface to study its interior. The sun vibrates constantly. These vibrations are caused by pressure waves, or P modes, bouncing around inside the sun. When we observe the sun carefully, especially with instruments that detect tiny shifts in light caused by motion, we can map how these waves travel. Some waves penetrate deep into the core, others skim along the outer layers. By measuring the timing, speed, and frequency of these oscillations, scientists can infer the temperature, composition, and motion inside the sun, without ever having to look inside directly. The Solar and Heliospheric Observatory, SOHO, has been instrumental in this work. Launched in 1995, it carries a suite of instruments that allow us to detect these vibrations and build three-dimensional maps of the sun's interior structure. This data has confirmed the location and size of the convection and radiative zones and has revealed how rotation changes with depth. Faster at the equator, slower near the poles. These rotation patterns are especially important. They play a central role in generating the sun's magnetic field. The solar dynamo, the mechanism that converts motion into magnetism, is believed to operate at the boundary between the radiative and convective zones, a region known as the tachocline. Here, differential rotation creates powerful shearing forces, twisting magnetic fields and building the complex, ever-changing magnetic structure that drives solar activity. Above the photosphere, we find the chromosphere, a thin and relatively cool region, though still thousands of degrees hotter than Earth's surface. When viewed during a solar eclipse, the chromosphere appears as a thin red ring surrounding the sun. This color comes from the hydrogen atoms emitting a specific red wavelength known as H-alpha, which is often used in solar imaging to reveal flares and filaments. Above this lies the corona, the sun's outermost atmosphere. The corona is full of paradoxes. It is faint, tenuous, and surprisingly hot, reaching temperatures of over 1 million degrees Celsius. This heating is still not fully explained. It's one of the major mysteries in solar physics. Why does the temperature increase as we move away from the surface? One of the leading theories involves magnetohydrodynamic, MHD waves. These are waves of plasma and magnetic fields that travel from the lower solar atmosphere into the corona. As these waves dissipate, they may deposit energy, heating the surrounding gas. Another possibility is magnetic reconnection, when magnetic field lines break and reconnect, releasing bursts of energy that heat the surrounding plasma. Understanding coronal heating is a major goal of solar missions like NASA's Parker Solar Probe and ESA's Solar Orbiter. These spacecraft are moving closer to the sun than ever before, flying through the corona itself. Parker is on a series of increasingly close orbits, eventually bringing it within just 6 million kilometers of the solar surface. At that distance, it will be directly sampling the environment where the corona forms and the solar wind accelerates. These missions are already transforming our understanding of the sun. Parker Solar Probe has detected unexpected structures in the solar wind. Switchbacks, sudden reversals in magnetic field direction that may be linked to the processes that heat and accelerate solar particles. Meanwhile, Solar Orbiter has taken the closest images ever of the Sun's poles, revealing patterns of magnetic activity we've never seen before. The poles of the Sun are especially mysterious. From Earth, we always view the Sun from near its equatorial plane, but the polar regions may hold critical clues to the solar cycle and magnetic reversals. The global magnetic field flips every 11 years, but this process begins at the poles. Studying the polar magnetic fields can help scientists forecast the strength and timing of future solar cycles. Vital information for understanding space weather. Space weather, the impact of solar activity on Earth and near-Earth space, is an increasingly important field. As our society becomes more dependent on satellites, telecommunications, and power grids, understanding and predicting space weather events becomes not just scientific curiosity, but practical necessity. Severe solar storms can damage satellites, disrupt radio communications, and even induce currents in electrical systems on the ground. One way we monitor these events is by observing the Sun's magnetograms, maps of magnetic fields on the solar surface. Areas with strong magnetic concentrations, especially regions of opposite polarity close together, are potential flare and CME sources. By tracking these regions in near real time, solar physicists can issue alerts when flaring is likely. Coronal mass ejections, CMEs, can take from 15 hours to several days to reach Earth. During that time, space weather agencies monitor their speed, direction, and magnetic orientation. If a CME's magnetic field is oriented opposite to Earth's magnetic field, the interaction will be much more intense, leading to stronger geomagnetic storms. Understanding this orientation is key to forecasting the severity of an event. Solar observation also relies heavily on spectroscopy. When we spread sunlight into its component colors, we get a spectrum, a rainbow of light, with dark absorption lines at specific wavelengths. These lines correspond to the elements in the Sun's atmosphere. Each element absorbs light at particular wavelengths, acting like a fingerprint. By analyzing these spectra, scientists determine not only what the Sun is made of, but also how the plasma is moving. The Doppler effect causes the spectral lines to shift slightly, depending on whether material is moving toward or away from us. This technique is used to track plasma flows, sunspot dynamics, and wave propagation across the solar disk. One of the remarkable discoveries from spectroscopy is the presence of heavy elements in the solar atmosphere. Elements like iron, oxygen, and carbon. These elements were not formed in the Sun, but inherited from earlier generations of stars. Before our Sun existed, other stars lived, fused elements in their cores, and exploded in supernovae, scattering those elements into space. Our Sun formed from that enriched material. This means that the Sun is part of a cosmic lineage, a descendant of stars that came before, and the source of elements that now form planets, oceans, and life. Every atom of calcium in your bones, iron in your blood, and carbon in your cells once passed through a star. The Sun's own fusion creates helium from hydrogen, but its formation was built upon stellar generations stretching back billions of years. Right now, the Sun sits comfortably in the main sequence stage of its life, a period of stability that defines the vast majority of a star's lifetime. In this phase, hydrogen nuclei fuse into helium in the core, releasing vast amounts of energy in the form of radiation and heat. This energy supports the Sun against the force of gravity, creating a balance known as hydrostatic equilibrium. But this balanced state hasn't always existed, and it won't last forever. Let's rewind about 4.6 billion years to the Sun's beginning. The Sun, like all stars, formed from a giant molecular cloud, a vast region of cold gas and dust drifting through space. These clouds are mostly made of hydrogen molecules with small amounts of helium and trace elements. Though they are sparse by terrestrial standards, these clouds contain enough material to birth entire stellar systems. Something, perhaps the shock wave from a nearby supernova, triggered a region of the cloud to collapse under its own gravity. As it fell inward, it began to spin, flattening into a rotating protoplanetary disk. At the center of this disk, gas and dust compressed into a growing sphere, the protostar that would become the Sun. As the protostar contracted, it heated up. Gravitational potential energy was converted into thermal energy. Eventually, the core reached a critical temperature and pressure, around 10 million degrees Celsius, at which point nuclear fusion ignited. Hydrogen atoms began to fuse into helium, releasing energy and light. At that moment, the Sun was born. The leftover material in the disk formed the planets, moons, asteroids, and comets of the solar system. The inner, hotter region of the disk gave rise to rocky planets like Mercury, Venus, Earth, and Mars. The outer, cooler parts allowed gas giants and icy worlds to form. All of this material, the planets and the Sun itself, came from the same original cloud, meaning everything in the solar system shares a common origin. Once fusion began, the Sun entered the main sequence, where it has remained for billions of years. This phase is characterized by steady energy output and a stable structure. But even during this seemingly unchanging time, the Sun is slowly evolving. The core accumulates helium, which doesn't fuse at main sequence temperatures. As helium builds up, the core contracts and heats, causing the outer layers of the Sun to slowly expand and brighten. In fact, the Sun is about 30% brighter now than it was when life first appeared on Earth. This gradual increase in luminosity is slow enough that life on Earth has had time to adapt. But in the very distant future, it will have profound consequences. In about 1 billion years, the Sun's increased brightness will raise Earth's surface temperature enough to disrupt the carbon cycle, leading to the loss of oceans and the eventual sterilization of the planet. Even before the Sun reaches its red giant phase, Earth may become uninhabitable due to the slow march of solar evolution. But what happens after the Sun exhausts its supply of hydrogen in the core? When hydrogen fusion slows, the delicate balance of hydrostatic equilibrium breaks down. The core, no longer supported by fusion pressure, begins to collapse under gravity. As it compresses, it heats up even more, igniting hydrogen in a shell around the core. This causes the Sun's outer layers to expand dramatically. Over a relatively short astronomical timescale, perhaps a few 100 million years, the Sun will swell into a red giant. As a red giant, the Sun will become enormous, possibly expanding beyond Earth's current orbit. Whether it actually engulfs our planet depends on a variety of factors, including mass loss and tidal interactions. At the very least, Earth's surface will be scorched and stripped of its atmosphere. The inner planets will be drastically altered or destroyed. Inside the red giant, the core continues to shrink and heat until it reaches temperatures high enough for helium fusion. This process, known as the helium flash, happens suddenly and dramatically. Helium atoms fuse into carbon and oxygen, releasing a new burst of energy that stabilizes the star again, for a while. This phase, however, is short-lived. Helium burns faster than hydrogen, and the core soon accumulates carbon and oxygen. For a star of the Sun's mass, the core temperature will never become high enough to fuse these heavier elements. Once helium runs out, no further fusion can occur in the core. Gravity takes over again, collapsing the core into an incredibly dense, Earth-sized object known as a white dwarf. As the outer layers are shed into space, they create a beautiful structure known as a planetary nebula. This glowing shell of ionized gas is lit from within by the radiation of the hot core. These nebulae are often symmetrical, colorful, and complex, like cosmic flowers blooming in the dark. Eventually, the white dwarf cools and fades over billions of years, leaving behind only a cold, inert remnant. This entire sequence, from protostar to white dwarf, is the fate of all low to medium mass stars like the Sun. It's a quiet ending compared to the explosive deaths of massive stars, which become supernovae and neutron stars or black holes. Still, in its own way, the Sun's end is spectacular, painting the sky with light one last time before fading into darkness. But even as it dies, the Sun gives back to the universe. The elements formed during its lifetime, helium, carbon, oxygen, are returned to space in the planetary nebula. These atoms will drift through the galaxy, perhaps to become part of another star, another planet, or even another form of life. The story of the Sun is not just its own, it is part of a grand cosmic cycle. Astronomers today study stars at every stage of this cycle to piece together the story. Using powerful telescopes like the James Webb Space Telescope and ALMA, scientists observe star-forming regions, aging red giants, planetary nebulae, and white dwarfs across the galaxy. Each observation helps refine our models and gives new insight into our Sun's past and future. Meanwhile, the Sun continues its steady rhythm, rising and setting, cycling through its magnetic phases, sending light and warmth across space. To us, it is the source of days, seasons, energy, and life. But from a broader perspective, it is a middle-aged star quietly traveling through the Orion arm of the Milky Way. The Sun orbits the center of the galaxy once every 225 to 250 million years, a journey known as a galactic year. During that time, stars are born and die, civilizations may rise and fall, and new worlds come into being. Our solar system has completed only about 20 such galactic years since it formed. We often think of the Sun as stationary, but it's not. It moves at roughly 828,000 kilometers per hour, dragging the planets along with it, tracing a spiral path through the galaxy. Around it, the heliosphere provides a shielded environment, creating a protective bubble in a galaxy filled with radiation and interstellar matter. The solar system's journey through the galaxy can even influence Earth's climate and biodiversity. Some scientists speculate that as we pass through dense regions of the Milky Way, cosmic rays might increase, subtly affecting cloud formation or even contributing to mass extinction events. The relationship between the Sun's motion and Earth's history is a rich and ongoing field of study. Yet despite its movement, the Sun remains our constant. For ancient cultures, it was the chariot of a god, the eye of heaven, the great giver of life. Today, we understand it as a dynamic fusion reactor, a magnetic puzzle, and a subject of relentless observation and curiosity. And still it shines, never ceasing, never resting, always burning. This deep look into the Sun's past and future reminds us of the vast timescales of the universe. Human history is a blink in the eye of stellar evolution. But in that blink, we've gone from watching sunrises to building spacecraft that touch the edge of the corona. We've gone from stories of sun gods to simulations of stellar magnetism, from sundials to solar panels. Our connection to the sun has evolved, but never faded. It is more than our star. It is our beginning, our clock, our furnace, and our future. In the not-so-distant past, our understanding of the sun was limited to what we could observe from Earth's surface. Telescopes showed sunspots, eclipses revealed the glowing corona, and early spectroscopy hinted at the sun's chemical makeup. But today, we are entering a golden age of solar science, a time when new tools and missions are allowing us to see the sun with unprecedented detail and depth. Much of this progress has come from going beyond Earth's atmosphere. The atmosphere filters out many wavelengths of light, including ultraviolet and X-rays, bands that are critical for studying the sun's hottest and most dynamic features. So scientists launched observatories into space, where they could peer into the sun's invisible light. One of the most transformative missions in this regard has been the Solar Dynamics Observatory, SDO. Launched by NASA in 2010, SDO continuously monitors the sun in extreme ultraviolet light, taking full-disk images in 10 different wavelengths every few seconds. These images reveal the ever-changing loops, flares, and waves of plasma that dance through the solar atmosphere. SDO has allowed us to watch solar flares erupt in real time, see magnetic fields twist and snap, and observe the fine structure of sunspots as they evolve. It has also contributed to our understanding of how the sun's interior motions drive the magnetic activity that affects space weather. Complementing this work is SOHO, the Solar and Heliospheric Observatory, launched in 1995. Orbiting at the Lagrange point between Earth and the Sun, SOHO has been operating for decades, helping track sunspots, monitor solar wind, and even discover comets. In fact, SOHO holds the record for discovering the most comets in history, over 4,000, thanks to its ability to detect their bright trails as they skim past the sun. Then there's STEREO, the Solar Terrestrial Relations Observatory, a pair of spacecraft launched in 2006 that provided our first three-dimensional views of the sun. By placing the two spacecraft on opposite sides of the sun, STEREO allowed scientists to track solar eruptions from multiple angles and observe how CMEs expand and move through space. These missions helped lay the foundation for what came next, an era of truly deep solar exploration. In 2018, NASA launched the Parker Solar Probe, a mission designed to fly directly into the sun's corona. No spacecraft has ever gone so close. Parker is expected to make a series of progressively tighter orbits using gravity assists from Venus to bring it closer and closer to the solar surface, eventually within just 6 million kilometers of the photosphere. At these distances, Parker will fly through the outermost layers of the corona, sampling the solar wind at its source and measuring the magnetic fields, particles, and waves that drive it. It will answer questions that have puzzled scientists for decades. Why is the corona so much hotter than the surface? How is the solar wind accelerated to such high speeds? What role do switchbacks and magnetic turbulence play? Even before reaching its closest approaches, Parker has already made profound discoveries. It found that the solar wind is not smooth, but structured, full of kinks and folds, including switchbacks where the magnetic field briefly reverses direction. These features may be part of the mechanism that heats the corona and launches the solar wind, and their discovery has opened a new chapter in solar physics. Another groundbreaking mission is Solar Orbiter, launched by the European Space Agency in collaboration with NASA. Unlike Parker, which flies through the corona itself, Solar Orbiter is equipped with high-resolution cameras to observe the Sun from a safe distance. It carries both remote sensing instruments to take detailed images and in situ instruments to measure particles and fields. Solar Orbiter's most important feature is its highly tilted orbit, which will gradually allow it to view the Sun's polar regions, areas we've never seen directly. The Sun's poles are crucial to understanding the magnetic cycle. It's here that magnetic field lines converge, reverse, and flow into the heliosphere. Solar Orbiter will help answer how the solar cycle starts and why it varies in intensity over time. These missions are complemented by a network of Earth-based solar observatories. One of the most powerful is the Daniel K. Inouye Solar Telescope, DKEST, in Hawaii. With a 4-meter mirror, the largest ever used for solar observation, DKEST provides stunning close-ups of the solar surface. Its resolution allows scientists to see details as small as 30 kilometers across, which is like spotting a granule on the Sun the size of a large city. DKEST has revealed the fine-scale structure of granulation, the pattern of rising and falling plasma caused by convection. It has also observed the behavior of magnetic fields at the smallest scales, capturing how tiny magnetic loops emerge, twist, and merge into larger structures. These insights help link small-scale magnetic activity to large-scale solar phenomena, like flares and CMEs. Collectively, these observatories form a multi-perspective, multi-wavelength approach to solar science. From radio waves to gamma rays, from ground-based telescopes to interplanetary probes, we now study the Sun across the entire electromagnetic spectrum and from every angle imaginable. We are also entering the era of machine learning in solar science. The vast volume of data generated by missions like SDO and DKIST is too large for humans to sift through manually. So scientists are training artificial intelligence to detect patterns, predict solar flares, and recognize precursors to major space weather events. These tools can analyze years of solar images in seconds, offering a new way to understand the Sun's rhythms and anomalies. Meanwhile, the data collected by these missions feeds into global efforts to predict solar activity. Forecasting space weather is still in its early stages, but progress is being made. Models now simulate the entire Sun-Earth system, from magnetic field lines on the solar surface to the effects on Earth's ionosphere and power grids. These models incorporate real-time satellite data to issue warnings for geomagnetic storms, helping protect vital systems. As we prepare for future space missions, including potential long-term settlements on the Moon and Mars, the need to understand the Sun becomes even more urgent. Outside of Earth's magnetic protection, astronauts face a harsh environment filled with radiation. A sudden solar particle event, SPE, could pose a serious threat. Accurate solar forecasting will be essential for human exploration beyond Earth. In response, space agencies are planning next-generation missions. These include proposals for spacecraft that can continuously image the far side of the Sun, deep space observatories positioned at Lagrange points, and probes that could explore the outer heliosphere in greater detail. There's even talk of developing solar sail missions that could maintain constant views of high-risk active regions by hovering in artificial orbits between Earth and the Sun. In parallel, solar power remains a major technological frontier. From satellites in orbit to solar farms on Earth, we are learning how to convert sunlight into electricity more efficiently. Research into solar panel materials, solar concentrators, and even space-based solar power continues to grow, linking solar science to renewable energy and climate solutions here on Earth. Perhaps most profoundly, solar science represents a triumph of human curiosity. For thousands of years, people watched the sun rise and set, felt its heat on their skin, and wondered what it was. Today, we build spacecraft that fly into its atmosphere and return data in real time. We transform photons into pixels, magnetic fields into maps, and data into understanding. And the more we learn, the more we realize how much is left to explore. There are still mysteries that resist explanation. Why does the corona heat up instead of cooling with distance? What causes the exact timing and strength of solar cycles? How do localized magnetic events cascade into large-scale eruptions? These are not only fascinating puzzles, they are essential for protecting satellites, astronauts, and even the electrical systems that power our daily lives. The sun is no longer just a subject of myth and wonder. It is a living laboratory of plasma physics, thermonuclear fusion, and magnetohydrodynamics. And as we peer deeper than ever before, with telescopes, probes, and algorithms, we are not only seeing the sun more clearly, we are seeing ourselves, our needs, our future, and our place in the solar system. The quest to understand the sun is one of humanity's greatest scientific adventures, and we are just getting started. At the heart of the sun lies a powerful engine, an inferno so intense that matter itself is broken down into its most basic components. This is the realm of nuclear fusion, the process that powers the sun and sustains life on Earth. Let's begin at the very center. The sun's core is a region about 25% of the solar radius, where temperatures soar to over 15 million degrees Celsius and pressures exceed 250 billion atmospheres. Under these extreme conditions, hydrogen nuclei, protons, move so rapidly and are packed so tightly that they collide and stick together, overcoming their natural electrostatic repulsion. This is not the kind of burning we associate with fire. It's something far more fundamental. In the core, hydrogen nuclei fuse to form helium, releasing enormous amounts of energy in the process. The specific pathway through which this occurs is called the proton-proton chain. Here's how it works. First, two protons fuse to form deuterium, a rare isotope of hydrogen with one proton and one neutron. This reaction releases a positron and a neutrino, a nearly massless particle that barely interacts with anything. Then, another proton collides with the deuterium to form helium-3, which contains two protons and one neutron. Finally, two helium-3 nuclei collide to form a stable helium-4 nucleus, releasing two protons in the process. Each step in this chain releases energy in the form of gamma-ray photons and kinetic energy. Though the amount of energy from a single fusion reaction is tiny, the sheer number of reactions, around 10^38 every second, adds up to produce the sun's immense luminosity. The energy generated in the core doesn't travel directly to the surface. Instead, it takes a long, winding journey through the radiative zone, where energy is transferred via radiation. Here, photons are constantly absorbed and re-emitted by charged particles, bouncing randomly in all directions. This random walk slows the progress of energy so much that a single photon can take up to 100,000 to 1,000,000 years to travel from the core to the outer layers. As the energy moves outward, it eventually reaches the convective zone, where rising and falling currents of hot plasma carry energy the rest of the way to the surface. This process is far more efficient than radiation, and it gives rise to the bubbling, granular texture of the photosphere, which we can observe with high-resolution telescopes. The energy that escapes from the photosphere is what we see and feel as sunlight. Every beam of light that touches Earth began its journey in a fusion reaction deep inside the Sun, created by the same process that powers stars across the universe. But nuclear fusion in the Sun is not just about energy, it also transforms matter. Over billions of years, hydrogen is steadily converted into helium. This slow change in composition is altering the Sun's internal structure, core density, and fusion rate. The Sun's hydrogen fuel is not infinite, and though there is plenty left, the process is irreversible. Eventually, the core will become so helium-rich that fusion of hydrogen can no longer continue in the same way. Fusion is what makes the Sun a star, and it's also what made life possible. The sunlight that fuels photosynthesis, warms oceans, drives weather, and lights our days is a direct byproduct of this reaction. Without fusion, there would be no heat, no light, no energy to power our world. Understanding fusion has also helped us decode the chemical makeup of the Sun. Spectroscopy, splitting light into its component wavelengths, allows us to identify which elements are present in the solar atmosphere. The Sun is mostly hydrogen and helium, but it also contains small amounts of heavier elements like oxygen, carbon, neon, nitrogen, magnesium, iron, and silicon. In astrophysics, anything heavier than helium is referred to as a metal, regardless of its properties on Earth. The Sun's overall metallicity, the proportion of elements heavier than helium, is relatively low, but not zero. This is important. It tells us that the Sun is not a first-generation star formed from the pristine hydrogen of the Big Bang. Instead, it is a second or third-generation star, born from the remnants of earlier stellar generations that exploded and returned their elements to the interstellar medium. These elements were formed in massive stars and supernovae, spread across space, and eventually incorporated into the molecular cloud that became the Sun and solar system. In this way, the Sun is a kind of cosmic heir, a descendant of long-dead stars, now giving rise to new worlds and new forms of life. The precise measurement of solar composition has also given rise to a fascinating puzzle known as the solar neutrino problem. When scientists first began detecting neutrinos, those elusive particles produced during fusion, they found only about 1/3 the number that theoretical models predicted. This discrepancy was deeply troubling, and for decades it remained unresolved. Eventually, the answer came not from changing our understanding of the Sun, but from deepening our knowledge of neutrinos. It turned out that neutrinos oscillate. They change flavors as they travel through space, shifting between electron, muon, and tau types. Early detectors were only sensitive to one type, missing the rest. When newer, more advanced detectors were built, the full count matched expectations. The solar neutrino problem was solved, and in the process we discovered new physics beyond the standard model. This is one example of how studying the Sun leads to breakthroughs in fundamental science. By trying to understand our nearest star, we've learned about particle physics, quantum tunneling, plasma behavior, and the very forces that hold atoms together. The Sun is not just a subject, it's a proving ground for the laws of nature. Fusion, in particular, has inspired decades of research into fusion energy on Earth. If we could replicate the Sun's power source in a controlled, sustained way, we could solve many of our energy problems. Fusion fuel, like deuterium, is abundant, and the process produces no greenhouse gases, or long-lived radioactive waste. However, achieving the temperatures and pressures needed for fusion is extraordinarily difficult. Projects like ITER, the International Fusion Experiment in France, aim to demonstrate that net energy can be produced from fusion reactions. Though we are not there yet, progress is steady, and each advance brings us closer to harnessing the same power that fuels the sun. The sun's fusion process also serves as a cosmic standard candle. By studying the fusion rates, luminosity, and spectral output of the sun, we can compare other stars to it. This helps astronomers determine the ages, distances, and compositions of stars across the galaxy. The sun is our baseline, a familiar light by which to understand the unfamiliar. And yet, even the sun still holds mysteries. We know the basic fusion cycle, but questions remain about how mixing occurs in the core, how fusion rates subtly fluctuate over time, and how they correlate with surface activity. Are there unknown processes occurring deep within the solar interior? Are we seeing the whole picture, or just a surface reflection of a more complex mechanism? Studying the fusion process has also refined our understanding of stellar evolution. Depending on a star's mass, fusion proceeds along different pathways. In more massive stars, the CNO cycle, involving carbon, nitrogen, and oxygen as catalysts, dominates over the proton-proton chain. In still larger stars, elements are fused into progressively heavier nuclei, eventually forming iron, the point beyond which fusion no longer releases energy. The sun, by contrast, will never reach those stages. Its core will never become hot enough to fuse carbon or oxygen. When it dies, it will not explode in a supernova or collapse into a black hole. Instead, it will gently shed its outer layers, leaving behind a white dwarf, a quiet ember of fusion long extinguished. Still, that gentle ending doesn't make the sun's story any less important. From fusion to light, from atoms to life, the sun is the engine that makes our world possible. Its nuclear heart beats steadily, unseen but vital, transforming matter, shaping space, and sustaining life across the ages. Long before telescopes or spacecraft, before equations or electricity, humans looked up at the sun with awe and reverence. It was the giver of warmth, the ruler of the day, and the most consistent presence in the sky. The sun's rising and setting structured time itself. Its annual journey marked the seasons, guided agriculture, and shaped the rhythms of life and ceremony. Across cultures and continents, ancient civilizations created powerful mythologies around the sun. In Egypt, the sun was Ra, the supreme god who sailed across the sky in his celestial boat, only to journey through the underworld each night. In Aztec tradition, the sun was Tonatiuh, a deity who demanded sacrifices to keep moving through the heavens. The Inca worshipped Inti, the sun god and divine ancestor of their rulers, who was central to both governance and ritual life. These solar deities weren't just symbols, they were embodiments of natural order, cosmic power, and life itself. Temples, pyramids, and entire cities were aligned with the sun's movements. The Mayan civilization built observatories to track solar eclipses and equinoxes with astonishing accuracy. In Europe, Stonehenge captured the midsummer sunrise and midwinter sunset. Around the world, solar calendars emerged, marking solstices, planting seasons, and times of celebration or mourning. But the sun wasn't just a god, it was a mystery. Ancient thinkers asked profound questions. What is it made of? Why does it move across the sky? Could it be a fire, a hole into the heavens? The earliest scientific theories of the sun emerged in classical Greece. Anaxagoras proposed that it was a glowing rock. Aristarchus of Samos guessed, centuries ahead of his time, that the Earth revolved around it. Yet for over 1,000 years, the dominant cosmology placed Earth at the center, with the Sun orbiting us in perfect circles. It wasn't until the 16th century that Nicolaus Copernicus reignited the heliocentric model. His theory, placing the Sun at the center of the solar system, was revolutionary and dangerous. It challenged not only scientific ideas, but religious and philosophical assumptions about humanity's place in the universe. The work of Galileo Galilei provided early observational support for this new vision. With his telescope, Galileo discovered sunspots, dark, transient blemishes on the solar surface. These were shocking to those who believed the heavens were perfect and unchanging. Galileo's sketches of sunspot motion offered early evidence that the Sun rotated, but his insistence on heliocentrism led to house arrest, a fate many early astronomers risked in pursuit of the truth. In the centuries that followed, the scientific revolution transformed our understanding of the Sun. Isaac Newton described how gravity governed the orbits of planets around the Sun. William Herschel studied solar cycles and suggested that sunspots might affect Earth's climate. Spectroscopy emerged in the 19th century, revealing that sunlight could be broken into a rainbow of colors, each line in the spectrum representing a different chemical element. In fact, it was in the Sun that a new element was first discovered. In 1868, scientists observing a solar eclipse detected an unknown yellow spectral line. They named the element helium, after Helios, the Greek personification of the Sun, long before helium was ever found on Earth. By the early 20th century, physicists were still grappling with a fundamental question. What powered the Sun? Chemical combustion couldn't explain its enormous and sustained output of energy. The answer came from the emerging science of nuclear physics. Albert Einstein's famous equation, E = mc2, showed how mass could be converted into energy. Later, Hans Bethe and others worked out the details of nuclear fusion, finally solving the mystery of the Sun's power source. The discovery of fusion changed everything. It linked the Sun to the broader story of the universe. Stars, it turned out, were not just points of light, but forges of matter, cosmic crucibles where the elements were born. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created in the hearts of stars like the Sun, or in the violent deaths of stars far more massive. In the modern era, the Sun has become not just an object of curiosity or worship, but a subject of precision science. Space agencies have launched missions to study it in every wavelength and from every angle. Data flows continuously from solar observatories, filling vast archives with petabytes of imagery, spectra, and telemetry. And yet, despite all our progress, the Sun still holds our imagination. It still inspires poets and painters, philosophers and dreamers. It still defines our days and guides our lives. And it still challenges scientists with questions as deep and complex as any ever asked. Why does the Sun have an 11-year cycle? Why does its corona reach millions of degrees? What causes sudden magnetic flips, powerful flares, or the puzzling flows inside its convection zone? Each answer we uncover leads to new mysteries and new connections. The Sun is also a reminder of impermanence. The light we see today left the Sun 8 minutes ago, a message from a past moment traveling across space to reach us. The surface we observe is always changing. The light is always shifting. Even the Sun's seemingly eternal glow is the result of processes that will eventually come to an end. And yet, in that impermanence is constancy. For billions of years, the sun has risen over Earth, watched continents drift, climates change, and species evolve. It has seen the rise of human civilization, the birth of language, the construction of cities, and the launch of spacecraft. It has shone on cave walls and touch screens, on deserts and satellites. Our relationship with the sun has always been one of curiosity and dependence. As children, we draw it with yellow rays. As scientists, we model its magnetic fields in supercomputers. As explorers, we send machines to kiss its corona. We look up, and it is always there, watching, waiting, burning. In many ways, our journey as a species has mirrored our growing understanding of the sun. From myth to measurement, from ritual to radiation, we've moved from wonder to inquiry, and from inquiry to insight. But the wonder remains, because no matter how much we know, the sun is still the fire at the center of everything. It lights our way, it feeds our bodies, it powers our tools, and it fuels our dreams. As we come to the end of this journey into the heart of the sun, let's pause and reflect on just how much this one star means. The sun is not just a ball of hot plasma. It is not just a distant object in the sky. It is a force that shapes reality itself. Its light powers the chemistry of life. Its gravity anchors every planet, asteroid, and comet in motion. Its magnetic field sculpts invisible waves across space, and its storms ripple through the solar system, touching satellites and signals here on Earth. It is the furnace in which atoms were fused, and the reason we see colours, feel warmth, and know time. It rises and falls each day, never quite the same, yet always dependable. A quiet rhythm that has watched over our species from the beginning. Through stone tools, sailboats, telescopes, and rockets. Through myths and models, through questions and discoveries. And we're still learning. Every mission we send, every instrument we build, every equation we solve brings us closer to understanding our star, and in doing so, our own place in the universe. We've now touched the sun's atmosphere with spacecraft like Parker Solar Probe. We've seen the surface in more detail than ever before. We've begun to predict its moods and measure its pulses. Yet still, it holds secrets. Still, there are currents we haven't mapped, flares we can't fully forecast, cycles we don't yet comprehend. And so we keep watching, carefully, reverently, because the sun is not finished teaching us. Someday, far in the future, the sun will evolve. It will grow brighter, redder, larger. It will shed its outer layers and quietly collapse into a white dwarf, glowing softly in the darkness. The planets will have long since changed. Earth may be gone, or transformed, or moved, but the light the sun gave, its energy, its atoms, its influence, will echo on. Maybe in another star system, another creature will look up and wonder about their sun. Maybe they too will draw it on cave walls, build temples, or launch probes. Maybe they will trace their own atoms back to a star like ours. Because in the end, the sun is not only our star. It is an example of something more universal. A pattern written across the cosmos. A reminder that stars give birth, give light, give life. And that everything we are began in their hearts. So tonight, as you settle into rest, let that thought carry you, that you are, in every sense, made of sunlight, that your body, your breath, your thoughts are stitched together by particles forged in the fires of stars. The warmth on your skin, the rhythm of the seasons, the colours of a sunset, the golden light at the edge of the day, all of it born in a single, ordinary star that we have only just begun to understand. Sleep well, knowing that above you it still burns. Quiet, constant, alive. Thank you for spending this time with us here on Sleep Space. Good night.